Hello, welcome to Code Design. Today we'll be discussing one of my favorite data structure, which is disjoint set, is used for solving graph problems, and we can also call it union find. For the disjoint set has a data structure that we can call union find structure that maintains a collections of disjoint sets. So if you see why we are calling them disjoint sets, the element are not repeated. So all the elements can be only in one set. And this set are disjoint, that means you see there is no connection between this set, and this set. However, we are representing these sets as tree for better understanding, is basically for better understanding. And each of the set has a representative. So if you see for this set, 1 is pointing to 4 and 7 is pointing to 4. That means 4 is the representative of this set. This is having only one element, 5, and 5 is the representative of this set. And in this set, 6 is pointing to 3, linking to 3, and 3 is pointing to 2. So 2 is the representative for 6, and 8 is pointing to 3, and 3 is pointing to 2. So 2 is the representative for 8. So eventually 2 is the representative for the whole sets. So what disjoint set provide, why it is elegant comparing to other algorithm like DFS and BFS. So it has this data structure has two method, union or unite and find. For disjoint set, we can do them in O of log n time, where n is the number of elements. So this is the efficiency, and there is a technique called path compression. With path compression, we can even do it find and merge even in constant time. So as I will show how we do the path compression. So a graph, right? These could be elements of a matrix, or these elements could be from a graph, but based on where they connect, we can actually represent them as separate sets, disjoint sets. So as I said, 4 is the representative for this set, 5 is the representative of this set, and 2 is the representative of this set. And how we unite two sets, right? Say we want to unite this set and this set. So what we can simply do, we can have our strategy. So there is no fixed strategy to balance the tree, but a simple strategy could be to just to join the smaller set to the larger set. So here, this set has three elements and this has four. What we can do, we can point the representative of this set, which is 4, to representative of this set, which is 2. Now, 2 becomes the representative for the combined set or merged set. So we can call it also merged set. So to become the representative, so what is the element it had or size this set had? It had a size 3 and it had a size 4. So what would be the now the size for the new combined set? 4 plus 3 equals 7. So 7 elements. And the representative is 2. So, and using this strategy, the length of the path will be O of log n. So, if we have n elements, so the length of the path would be O of log n. So, we can find the representative of any element, right, in log n time. Um, um, so, let's see how we can implement these disjoint sets. So here is another example. There is a set of 1, 3, 5 with 3 element, and another set is 2 and 4. So we want to join these two sets, And what we can do, we can loop through 1 to n element. N is number of nodes. Here we have 5 elements. So we can declare an array with 5 elements, n elements, and for is basically n plus 1 with 0 as a default. So this with all these elements, what we can do, we can so what the link will represent, right? Link will represent what 5 is pointing to. Who is the parent, immediate parent of 5 is 1, right? Was the immediate parent of 3 is 1. So 5 and 3 is pointing to 1. Here 4 is pointing to 2. So and initially what we initialize them? Initialize each element with the same element. So initially we can say that 5 is representative of 5 is 5, representative of 3 is 3, considering they all are single set with one element. So we are can say representative of 5 is 5 or parent of 5 is 5, 4 is 4, 3 is 3. This is how we can initialize. And for the size, right? So we can initialize another array. We need to initialize size or rank. We can use size or we can use rank. If we use size, then we can say that um, we can initialize all of them with size 1. So 1 to 5 initialize with size 1. For we don't have element with 0, so is 0 default. So now let's see, after we initialize, how we can use the find operation. So to find element, what we need to do? Say we have one more element here. If we have one more element 6, which is point to 5, and we start the find operation here. So if give input is given here 6, x equals 6 for this, then while x not equals link of x. So what is link of x or parent of x? It is 5. So x is 6. So this satisfies. What we can do, x equals link of x. So x equals link of x means link of 6 equals 5. So now x is 5. Then we come again to the loop, and x is 5 and link of x. So x is 5 and link of x is 1. So which is not equal. So we can say x equals link of x. So now this x becomes 1. This x becomes 1. And then what is link of, again we come here, 1 not equals link of x, link of 1. So what is link of 1? Link of 1 is 1. If you remember, we just initialize every element with the same element as a representative. So it doesn't satisfy because now 1 is equals link of x, which is 1. So it breaks the loop and we return x, which is our 1. So this is how from this set having elements 1, 3, 5, 6, given a element 6, we get the representative of this set, which is 1 in log n time, n equals 4. Now, this is the regular find operation. There is a technique called path compression, but we haven't used the path compression yet. This is just find. So, for how can we identify if two elements like 6 and 4 belongs to the same set? So what we'll do, we can call find operation with 6. If it is 6, say find of 6, and we can call this find b, which is say 4, find of 4. What we find of 6 is 1. So representative of this is 1 and representative of this set is 2. So 1 not equals 2. So they are not same. They does not belong to the same set. They would be belonging to the same set. If we join these two sets, like if we connect this one, um, this set 2 with this one, then they will be connect point 2 to 1, then 1 would be the new representative of this set, and the same function will return true. For both 6 and 4, it will have representative 1. So let's see a C++ version of unite function. Why I'm saying a C++ version? For you is uses swap. C++ standard library STD has swap. So let's see, and we'll see also Java version. So when we want to unite these two sets, right? A, C, D, and B, E, F, G. So we need to find the representative of A. So say this is A, and what representative of A is A, because A is the representative. Um, and for B, say provided B, we find the representative of B is B, because B is the representative of this set. Now we have the size, right? When initialized, everything is size 1, but later the size will change, right? So what is the size of A would be 3, and the size of B would be 4. So size of A less than size of B. That means in this case, actually it's true. Size of less is less than B. So as I said, one simple strategy is to assign the smaller set to the larger set. So how we can do that? So here, if you see we are doing size of A plus equals size of B. That means we are assigning B to A, but A is smaller, right? So one simple trick can solve this problem. Let's swap A and B. So if we swap variable A and B, um, uh, A was holding A, and now this variable A will be holding B. And after the swap operation, A will be holding B, and B will be holding A. So we swap the value of these two operations. So now when I'm saying size of A is basically size of B. So size, because we swapped it. So size of B equals plus equals size of this would be A. So this would be B and this would be A. That means size of B, we are saying that 4 plus 3 equals 7. And link of B, right? So we swapped it. So link of B, B is now holding actually A. So it's basically link of A. Link of A would be pointing to B. So whatever is our this one will now point it to this set. So this is our new B is our new representative. So in this way, this will always ensure that the smallest set gets merged to the larger set, and the size of the larger set becomes the size of the two sets, summation of two sets, and the smaller set points to the larger set. So this is one way of, and this is like very short and concise way, good for competitive programming, and less things to handle. If you see that only few amount of code, but just you need to understand the swap thing, what's happening. It could be initially confusing. Now let's look another way. So if we are want to implement the same logic in Java, right? So what we cannot do, we cannot use swap method in Java or write a swap method, because for Java it is pass by value, not pass by reference. So if you create a swap method outside here and call the swap, it will not work, because this will not be recognized. The swap will not work because Java is passed by value, not passed by reference. So what we can do if we still want to, there is workaround like we can create an array and then pass the array to a swap method and then change the array index. But we don't need to do it. Just we can do the swap here. So we are doing the swap here, keeping A to a temp variable and assigning B to A and then assigning temp to B. So we are swapping it. So this works fine with Java. Just you do the swap here, and the rest of the thing is still same. Instead of link, I just use the array name as parent. That's the difference. Otherwise, is the same. So the same time complexity O log n. And there is path compression, right? What is path compression? How we can compress the path? So if you can see for G points to E and E points to B. So each time in you need to find the this one representative of this set for a element G. You need to go through for the our current implementation of find, right? You need to go through current implementation of find. You need to go through each of the element because from it is doing working like that. From G you need to go E and you need to B, so which will take log and time. But there is a efficient way that we can avoid this log and time and make it a constant or one time. So how we can do that? So while we're doing this loop, let's update the array indexes, array element. So how we do it? So similarly, if x equals link of x, if x is pointing to itself, that means it is the representative. Like as I said, like if you have only one element 5, so 5 is a representative of 5 itself. Or initially, even if you have multiple element 5, 1 and 4, 5, 1 and 4, when we initialize, we make representative 5 is 5, representative 1 is 1, and representative 4 is 4. So if we get it, then we return. Otherwise, we get link of x, we call the find of link of x. We call this recursively this find function with link of x. So say for 4, or let's do one more here, 5, 4, and here we have 2. So um, if we call this one is x equals 2, then what will happen? Link of x equals 4. So it's not x not equals 4. 2 and link of x is 4. So it will not return. Then it will come here. Link of x, that means link of x equals find of link of x. We call this find function recursively with these 2. So what happened? Now this x is 2. This x is 2. And then again, what no, actually, we call it this x is 4 now because we started with 2 and we find link of x, link of 2 equals 4. So we are calling this function now with 4. So when we call it 4, then what is parent of 4 is 5. So it's not equal. So again, we'll call this find with 4, not 4, with this x is 4, parent of 4, which is 5. We'll call this function with 5. So when we call this function with 5, 5 will be here. This time it will be 5, x will be 5. And what we say, link of x, link of 5 would be 5 because 5 is the representative and it will return 5. So while we're doing this, while this function will return, the last one will return to this one, right? The last one will return result to this one, and this one will return result to this one. So eventually what will happen, this link of x or this link of 2, the link of 2 would be 5 because the recursive call, right? It will keep returning. So it will return here and then it will return here. So finally, our link of x, we call initial link of 2 would be 5. So next time, link of 2 equals 5, right? So next time when we call the to find this representative of this element 2, we'll directly get 5. So which is constant time. So this is the beauty of path compression, which is very important part of this. So it makes log n even more efficient and constant time for the find and unite also. When find is constant, if you can find these two things in constant time, this one you find in one time, this one you find in one time, then actually even unite becomes constant time. So because unite you are just comparing the size or whatever it is, and you are just assigning. And those are constant operation. So let's see if we want to write our own disjoint set, the whole thing together. So how we can do it? So here, instead of link, we are using parent, an array of parent and array of rank. So we are using here rank instead of the size, because as I said, like there could be different strategy to maintain the um, um, tree, to maintain the tree, to balance the tree. We want the depth to be minimum for the tree, so that the find operation is efficient. So now we can use rank here. So what we are doing here, we are initializing, we are creating a parent with the n element with a parent array. We are creating the rank array with n element. And then we are looping through n and assigning parent of I equals I. That's what we have done, right? Representative of each element is the that in element, and we are making rank. We can make rank 0. That was size earlier what we have done. Now we initialize size 1, because size cannot be 0, because each state will have on at least that element. But this rank, we can assign 0 for all of the element. And then our find is same with path compression and union, right? So for union, we find representative of x, which is p1, we can call p1. Find representative of y, we can call p2. And if p1 not equals p2, right? So that means they are in different set. So if p1 equals p2, they are in same set. So if they are in same set, they are already united. So we don't need to unite them. If not, then only we need the union operation. So what it is doing is taking the rank of P1. So this set is checking the rank, and if greater than rank of P2. If rank of P1 is greater than rank of P2, then we are assigning parent of P2 to P1. That means we are actually making the representative of the set that is with higher rank. P1 in this case is higher rank. So we are assigning, making parent of P2 to P1. What if rank of P1 is less than P2? So we do the opposite. We say, since P2 is bigger, is having a bigger rank, the this set, the with representative P2. So we assign parent of P1 to P2. So with the bigger rank. And when they're equal, when ranks are equal, we can still what we are doing, we are still, if they are equal, we are assigning parent of P2 to P1 and simply increasing the rank of P1 because they are equal. So we could also do it for P2. So either of them, we just need to rank, increase rank for one of them and keep it consistent. So in this way, you can see have this disjoint set, and we can create object of this class and use it in our problems to solve. And there is one more approach. This is the last approach, but there could be so many other approaches you can you can find the union operation is implemented because the main goal is to have the tree balanced, and these data structure doesn't say some strict rule that you have to do this. So here, this implementation, we are using three parameters. So sometimes we need to have the size for some of the problem, um, like the Hackerrank problem. Uh, what is the problem? Roads and library. So roads and library, you will need to build roads. To find how many roads you have, you have to find how many nodes in a group. So the roads would be nodes minus one. So it's edges, right? N minus one edges. So in that case, you will need size. So and you can also have size, and you can have another extra array rank. So here you have three array. One is parent, another is size, and another is rank. So what you can do, you can initialize the size to one for all of them. Uh, Size of I, initially you can initialize to one for all of the element, and rank of I, you can initialize rank of I equals zero, making all the ranks zero. And um, what is our parent, right? Parent will still parent of I would be I, like initially all the element will refer to itself as a parent. So that would be the initializing for all element. Now on this union function, if p1 not equals p2, that means if they belongs, this p1 and p2 belongs to different set, then let's compare the rank. If rank of p1 greater or equals rank of p2, this is one option, right? Greater or equals. If greater, then we are doing the same thing. We are pointing parent of p2 to p1. So we are pointing p2 to p1 because p1 rank is higher, and p1 rank is higher. So size of p1 would be size of p1 plus size of p2. So cause is getting merged on p1. And here, what we can do, since size is important, here we are mentioning, we can disjoint set size making it zero is not necessary, is not required. But for some of the problem when you are dealing with size, you need to do that. Otherwise, you can get some malicious output. Now, so size of P2, we make it zero because now P2 is no longer the representative of the set because is getting merged to P1. And this is greater or equals, right? So when rank of P1 equals rank of P2, we increase the rank of P1. The same thing that we have done, the same approach. And this is the else option. Else means rank of P1 is less than rank of P2. That means rank of P2 is bigger. If P2 is bigger, then assign parent of P1 to P2 because P2 is bigger. And now the size, right? Now P2 is the representative because of the new set because P2 is bigger. So size of P2 would be size of P1 plus size of P2. And now that P1 is merged to P2, so you make size of p1 equals 0. So this is another way of doing it. So now that we have good understanding of design sets, how it works, what is the efficiency, you can try these problems for practice. I'll be making videos for each of them. A number of islands I have already done it with DFS and BFS. Maybe I can make one with a disjoint set. There is number of provinces, LeetCode 547, account march LeetCode 721, roads and library Hackerrank, satisfiability of equality equations, that is LeetCode 990, and there is one friendCircle which is from online assessment. Previously it was LeetCode 547. So I have a link here in my website springsoft.com. You can, I will also put it the link on the comment of this one, and the so yeah, and the site link and the comment link. So let me know if you like it or not. Thank you.